Okay, any questions from you first? If you remember, we had started studying the magnetic properties, the magnetic field, and to describe the magnetic field, we first discussed how we can measure the magnetic field. We can basically use a magnetic dipole. And we said that by a suitable choice of our currents, the magnetic dipole moment, a given magnetic dipole moment creates the magnetic induction, which can be written as, well, let's call it Pm, the magnetic moment, minus dot r hat divided by r cube, and the torque that this magnetic moment feels will be, the torque will be just the magnetic dipole moment cross the magnetic induction. So we can just use a magnetic dipole, which is basically a magnet, to determine the direction of the magnetic induction, because it will align itself with the magnetic induction. And once we have a magnetic dipole, to measure the magnetic dipole moment and the magnetic field, we can just do two experiments. In one of them, we just measure the oscillation frequency of the magnetic dipole around the direction of the magnetic field. That gave us a measurement of the magnetic dipole moment and the product of M and B. And we could also take a second magnetic dipole moment, put the original magnetic dipole moment perpendicular to the direction of the magnetic field, and put a second magnetic dipole at along the direction of the magnetic dipole moment, and measure the angle it makes with the magnetic direction of the magnetic field. That gave us a measure of the ratio of the magnetic moment and the magnetic dipole, magnetic induction. And from these two measurements, we could just determine the from these two measurements, we can determine the magnetic induction and the magnetic dipole moment. And then, okay, so that gives us a way of measuring these two quantities. And then the next task is, if now we have a way of measuring the magnetic induction, what creates the magnetic induction? And we said that basically we have the Biot-Savart law, and which was obtained by making many measurements, which says that if you have such a current, a line current, it will create a magnetic moment, magnetic induction at this point, let's say R. Let's say this, we can define a vector dl along this current carrying wire. And then the magnetic induction at the point R, created by this very small element, just turns out to be dB is 1/c. Well, this, we had said that this is a coefficient, the overall coefficient in this expression is some constant which has the units of inverse speed. So we just call that speed c, and so that overall constant is 1/c times I times dl cross r minus r prime divided by r minus r prime cube. Well, that, at least that factor related with the electric field is in fact quite similar to that part relating with the r and r prime is similar to the electric field expression, but there are important differences, like here we have a cross product of two vectors. If you remember, in the electrostatic case, we just have the charge, which was the source of the electric field, multiplied by that ratio of distances. Now, in this case, in the case of the magnetic induction, the source of magnetic induction is the current and dl, and the direction of the current is important, or in a sense, it's the moving charges. And it's not just the charges, but the product of charge times the velocity, which is the source of the magnetic induction. And this magnetic induction is perpendicular to both the dl and this radius vector. If you remember, in electrostatics, if you had a point charge, the electric field was along the line connecting this point charge to your observation point. But in the magnetic induction in this case is perpendicular to this line connecting this point charge. Well, we will have also studied the point charge and our observation point. It's perpendicular to that direction. And we also said that, okay, if we don't have just a line charge, but a flow of charges in a certain volume, we studied, since the charges are conservative, one thing we have to have is this had to be satisfied. So this basically tells the first term we can relate it to the amount of charge leaving or entering a given point. And the second term is just the flow of charges through a surface enclosing that region. So if the charges in a given region are decreasing, that is because there is a current running out of the surface, or if the charges in a given volume are increasing, that is if rho is increasing, that should mean that there is a current running into our surface. This is the expression of the conservation of charge. And this equation is called the continuity equation. And then we said that, okay, we have the continuity equation. If we have a region of space where the charges flow in electrostatics or in magnetostatics, we had all the time derivatives were zero. Nothing changes with time. That is the phenomena that we are studying at the moment. And hence the J should be divergence-less. Its divergence should be zero. And then we showed that if there is a region of space where the charges are flowing, not necessarily in a wire, they don't have to be in a wire, just have a bunch of charges and they are flowing in magnetostatics, they will also create a magnetic field. And we said that this flow of charge, we can imagine it as a collection of very thin wires carrying very small magnetic currents running through them. And when we just sum all of these, the magnetic fields created by all of these currents, when we divide this system into very thin wires, then we can use the Biot-Savart law. And just summing over all these wires, we could write the total magnetic induction as 1 over C times the current density at a given point cross R minus R prime divided by R minus R prime integrated over all possible values of R prime. This is, if we have a current density, this is the total magnetic induction. And finally, we said that if we have a point charge, well, in general, we said that J is nothing but at a given point, we can always write it in this form. And for a point charge, rho is nothing but Q located at the position of my charge. And then the magnetic induction, if you just put it in the above expression of the magnetic induction over here, B just turns out to be 1 over C Q V0, the velocity of my charge, cross R minus R0 divided by, here I have a cube, R minus R0 cube. There's a catch here, something we have to pay attention to. And sorry, we also wrote this in this form, Q V0 over C cross E at the point R. Now there was a slight catch, because you see, if rho is equal to Q Dirac delta R minus R0, and if this charge is moving, then del rho by del T would be equal to Q, the derivative of Dirac delta, times minus dr0 by dt, which is minus Q V0, the derivative of Dirac delta, which is definitely non-zero. But we said that in the static cases that we are studying, this derivative has to be zero. So this expression of the magnetic induction for a point charge, you will see it in many places, especially in books, in high school books. It is not true. It's only an approximation. We will also see other ways of deriving this expression from different perspectives. It's an approximation that is valid as long as you can treat this system as an magnetostatic system. Well, you can treat this system as a magnetostatic system if, oh, sorry, let me just rewrite this in a slightly different form. This is the gradient of Dirac delta. Well, we can write this, consider this system as a magnetostatic system if the velocity is slow. If V0 is sufficiently slow, in that case, we can treat it as a magnetostatic system, and this would be the approximate expression of the magnetic field. Of course, when we are talking about something being slow, we have to compare it with something else. Well, we don't know, but that constant c is kind of a characteristic speed related with magnetic phenomena, seems to be. So as long as V0, the speed is much slower than c, then this would be a good enough approximation. Then we would see that we have corrections that would come from the dynamic properties of the system. Okay, with that grain of salt, this is the magnetic field created by a point charge, and which we can also relate it to the electric field it creates. So you see, let's see, we have this point charge over here, which is moving in this direction with a velocity v0. Let's assume that it is creating this radial electric field. By the way, this is also not necessarily true, because a point charge creates this radially outward electric field in electrostatics. But this is not a static problem. But if we ignore any possible modification to this electric field, this will be the direction of the electric fields created by this point charge as it's moving. So if you look at the magnetic induction at that point, what will be the direction? Well, you see, the magnetic induction is parallel to V0 cross E. At this point, this is the direction of E. Well, V0 is always in this direction. So V0 cross E is out of the board. So this is the direction of magnetic induction. At this point, you see, this is the direction of E. This is still the direction of V0 into the board. So a kind of magnetic induction makes these circles around the direction of motion. At this point, this is E, this is V0, out. And in. So these magnetic induction just makes such circles as V's in that direction. Of course, assuming Q is positive.
All V's are equal? Or are all V's equal?
Well, you see, V0 is the velocity of the point charge. So the point charge has a single velocity, V0. You see, that is something you have to pay attention to here in this expression. V0 is the velocity. V0 is the velocity of the point charge. E of R is the electric field at the observation point. So they refer to two different points. V0 is the velocity at the position of the charge. Well, that's the only velocity we have. R is the position of our observation point. At that point, there's an electric field and a magnetic field. Let me make a foreshadowing at this point. Let me first write the force law. Now we will do some examples on how to calculate the total magnetic field later on. But basically, if you want to find the total magnetic field created by a current, you just take this Biot-Savart law, integrate it over all the current, and you are done. We had also, on Wednesday, we had also derived two relations that B field satisfies. We had seen that divergence of B is equal to 0, which also tells us that if you integrate this magnetic induction over any closed surface, this is always 0. But in the case of the electric field, if you remember, it told us that if you have the electric field integrated over a closed surface, it just gives us the total charges. Well, this basically tells me that there are no magnetic charges. There are no magnetic point charges. It's always zero. So-called magnetic monopoles do not exist, as far as we know. We wish they exist. I mean, it would answer a few of our quite difficult questions, but as far we couldn't yet manage to discover any. Now, for example, one of the questions that we do not know the answer of, why is the charge of particles quantized? Now, you see the quarks have charges, the 1/3 or 2/3 of the proton. So if you just take the 1/3 the charge of the proton as your quantum of electric charge, all the other charges we know are just integer multiples of 1/3 the charge of the proton. And there doesn't seem to be any reason for it to be so. So the question is why? Well, if there is a magnetic monopole, then we know why. Now, you will probably study it in quantum mechanics. But without a magnetic monopole, it seems to be hard to get an answer for that. And let's see, the other expression we obtained, the curl of B, if you remember in electrostatics, this was 0. But the curl of B, in this case, is 4 pi over C times J. Well, this is kind of nice. This seems to be the analog of Gauss' law in electrostatics, in the sense that this would allow us to obtain the magnetic induction, at least in simple systems, by just using simple symmetry arguments. So this would just correspond to B dot dl is equal to 4 pi over C times J dot dA over an area. And this is the boundary of the area. But J dot dA over an area just gives me the total current passing through that area. So B dot dl over any closed loop is just 4 pi over C times I enclosed. Well, let us just do an application of this one. Let's calculate the magnetic induction created by an infinite straight wire. So we will use this one, B dot dl is equal to 4 pi over C I enclosed. Of course, to be able to use, this is always true, but not always useful. To be able to be useful, we have to be able to evaluate the left-hand side for an unknown magnetic induction. For a general B, we cannot integrate it, because the idea of using this law would be just to use this to calculate B, but for an arbitrary B, the left-hand side we cannot integrate, and hence we can't solve it. So we have to know something about the magnetic induction to start with. So let's see. Let us look at this point. What is the direction of the magnetic induction? Well, let's just take a very small segment. This is my dl. This is the separation vector. dB, remember it is 1 over C times I dl cross that R over R cubed. So dl cross R is out of the screen. Or if you can just imagine this I as just a bunch of positive charges running downward. And we had already seen that the point charges just create these magnetic inductions that is circular around their velocity. Their velocity vector is along our wire. So the B is outside, pointing outward. On the other extreme, it will be pointing inward. So the magnetic induction just makes circles around our wire. Now, another thing is that our problem has this rotational symmetry. So if you rotate our system around this wire, nothing changes. So should be true for the magnetic induction. So we already know that magnetic induction is in the direction of, let's say, phi hat. The magnitude, the component, in principle, it can depend on phi, on Z, R, S, phi, and z, s being the distance from the wire. But we know that it cannot depend on phi because we have this rotational symmetry. It also cannot depend on z because we have the translational symmetry along the wire. So nothing should change if we translate our system along the z direction. So it basically tells me that the amplitude depends only on S. So this should be the form of the magnetic induction at an arbitrary point. So what is the collection of points for which S is a constant? A cylinder. Well, we need to have a closed loop. We can take a circle at any value of z. So we can just imagine such a circle. So I can integrate now b dot dl. Now dl is also in the phi hat direction. So this is nothing but b times dl. Around this circle, S is just constant. So Bs is a constant. I can take it out. What remains is just sum of, path integral. This line integral is nothing. You divide your line into very small segments. And for each one of the segments, dl is the length of that segment. I'm summing all those lengths. I obtain the total length of my closed loop. That is my circle. And hence it is 2 pi times S. This is b dot dl. Although I don't know what b is, I could evaluate the integral. This is kind of the trick. What is I enclosed? The total current passing through the area covered by this loop. I or minus I? How do we decide? Yes, the right-hand rule. It is plus I. So Bs is equal to 4 pi over C times I 1 over 2 pi S. Well, we can do some simplification. This is 2 over C I over S. Now we know the magnetic induction. Now, when we are using this law, we know that if we take any area, calculate the curl of any vector field, over some area, this is equal to the integral of C of the vector field over the boundary of that area. Of course, there are two things that we have to be consistent about. One is the direction of ds. The other one is the direction of dl. You see, if you have this any surface, ds is a vector in the normal to the direction of you just have your area divided into very small segments. At each segment you define a ds, and ds should be perpendicular to this area. You have two choices. You can make whichever one you like. Let's choose it upward direction. This is our direction of ds. Now the problem is we also have to choose the direction of dl consistently. And consist by consistently, I mean you use the right-hand rule. So if your thumb points in the direction of ds, your fingers curl in the direction of dl. So if we choose ds to be pointing upward, then dl has to be in that direction. That's the direction of my loop. So these two things have to be consistent for this equality to hold. In general, ds has these two possibilities. It can be either upward or downward. dl also has two choices, either clockwise or counterclockwise. But if they are consistent, and upward ds comes with a counterclockwise dl, and the downward ds comes with a clockwise dl. So that is something you have to pay attention to. Let us do one more example. Let us assume we have this infinite sheet. It carries a surface charge that's the sigma. It is infinite. It carries a surface charge that's the sigma. At the same time, it moves with a velocity, let's say v0. So we have moving charges. Well, the system doesn't change. It's an infinite flat plane. It is being translated along its translational symmetric axis. So it's a magnetostatic problem. In fact, it's even an electrostatic problem. Although the charges are moving, nothing is changed. So it's a static problem, basically.
What's the exam question? Electromagnetic course?
Which course?
You know.
Probably. But this is just a simple application. He didn't take that course. Well, we can, of course, we already know that there's a charge density, but this is not a volume current density. This is not a volume current density. We call this a surface current density. And the surface current density is just sigma V0. So if you just imagine, let's say, a very small line over there of length dl, then the total current running through that very small length is just k times dl. Of course, assuming k and dl are perpendicular to each other. If you want, we can just divide this into very small segments, or we can do something else. Let me just look at it from the side. The current, the surface current is into the screen. So it's just flowing like this. I just see it from this cross section. Now let us imagine this dl over there. I'm looking at the magnetic induction at this point, and also let's say at this point. Let us take a dl, and there will be a symmetrical dl over here. So what will be the magnetic induction created by this dl, the direction? The current is running into the screen. Just use your right-hand rule. You see, in this problem also, that's what we did. We had this infinite wire. The direction of the magnetic induction, we could determine it by the right-hand rule, used in the form that just your thumb points in the direction of I, then your fingers curl in the direction of the magnetic induction. So what is the direction of the magnetic induction? The contribution to the total magnetic induction at that point by this dl on the right. So what is the direction? Well, upward right. This is dl. So it is making circles around that dl. So it will be perpendicular to this dashed line. It will be in this direction. This is our dB. This is only the contribution from that dl. But we also have this dl over here. What will be the direction of the contribution of that dl on the left? It is the same length. Symmetrical in the sense that it will be symmetrical with respect to the horizontal plane. So it will be pointing in this direction, this angle being equal to this angle, and their magnitudes will be the same. So when you sum them up, the total will be in that direction. So for this configuration, we know that the magnetic induction above the plane is pointing from left to right everywhere. So this is our magnetic induction line. Below the plane, well, we can just repeat the same thing. So here, at this point, this will be dB. This will be the other dB. So the sum is in this direction. This will be true for any line segment that you can imagine on the left. So the sum will always be in the horizontal direction. So below that plane, it will be horizontal, and it will be in this direction. So let's say if we choose some axis, let's say this is x-axis, this is let me choose this as my x-axis, this is my y-axis, so that the z-axis is into the plane. So k is sigma v0 in the z-axis. Then the magnetic induction will be in the y-hat direction if z is larger than 0, minus y-hat direction if z is less than 0. And it will also have a magnitude which in principle can depend on x, y, and z coordinate. But you see, my problem has a translational symmetry along the y direction. Nothing changes if I translate my system along the y. That basically tells me that B cannot depend on y. It also has translational symmetry along the z-axis. Nothing changes if I translate my system along the z-axis. So again, nothing can depend on z. So that amplitude in the y-hat direction, it is either in one direction or the other direction, but it only depends on x.
What does it depend on x? I'm far away from an infinite plane to remain.
Let's see. Well, in principle, it can, in principle, it might depend on x, but we will see if it does or not. Well, we already had an example. For example, if we had an infinite charged surface, the electric field doesn't depend on the distance. Let's see if it will be the case here. Because you see, certain quantities do seem to depend on the distance from an infinite plane, like the potential of an infinite plane. That depends on the distance. Not the electric field, but the electrostatic potential does. So let's see what will happen here. So this was our K is into the screen. So let's just imagine, we have to imagine a closed loop. We know that it can depend on the x coordinate. So let's choose a loop which has a constant x, almost a constant x. So let's choose this loop. So this length is d, this is also d. Let's call this one L. And let's choose the direction of my loop to be in this direction. Once we choose a loop, we have to give it a direction. Let me give some names, A, B, C, and D. B dot dl around this loop will be equal to from A to B of B dot dl, from B to C, B dot dl, from C to D, B dot dl, and from D to A, B dot dl. And we know that B is Bx, it depends on x, let's say plus or minus, depending on where we are. No, sorry, this is not z, this is x. It depends on x in the y-hat direction. So as we go from B to C, the L is perpendicular to the y-hat direction from B to C, so this is 0. From D to A, B and DL, they are perpendicular to each other, that is also 0. So from A to B, it is B at minus D times L. That is the integral from A to B. The integral from C to D is B at D times minus L. Do you see why I took it minus L? Because we are going in the minus y hat direction from C to D. And this should be equal to (4 pi over C). What is the total current passing through this loop? Minus KL. Because if you just use the right-hand rule, out of the screen is the positive direction of the current. The current is running in the opposite direction, so it is a minus. And K is the current density. That is the surface current density. That's the current per unit length. So we have that length L within our loop. So it's just K dot L. So B of minus D minus B of D, if we just divide by L both sides, this is equal to minus 4 pi over C. K was sigma V0. Now furthermore, we just said that B of minus D should be equal to B of D. But that tells me that minus 2BD is minus 4 pi over C, sigma V0. I can cancel the minus 2's. B at the point D is 2 pi over C, sigma V0. So this is the magnetic induction, the component of the magnetic induction. Where? No. You see, B of minus D is equal to minus B of D. So on the left-hand side, I have minus 2. On the right-hand side, there's also another minus. So B of D, well, this basically tells me that above, this is the direction of the magnetic induction, because you see B of D is the component in the y-hat direction. So for x positive, above the plane, B of D, well, also, as you said, by the way, this is independent of D. So it's uniform.
What is the direction of Z hat?
Z hat, you see, it's in the direction of K, into the screen.
So what is the direction of K?
Into the screen in the Z hat direction. K is in the Z hat direction.
Why do we have on this side?
Because the positive you see, there we have the enclosed current. Enclosed current need not be positive in the Z direction. Enclosed current is positive if it is in the direction of our area vector. Now the area vector should be consistent with the direction of our loop. So in this problem, we are going around the loop in the counterclockwise sense. So the right-hand rule tells me that the current is positive if it is running in the minus Z direction. By the way, this is by nothing but V0 over C cross E. Magnitude. Let's see. Let me just redraw it. And furthermore, in fact, B is equal to V0 over C cross E. What is the direction of V0? V0 is inwards. At this point, what is the direction of E? Upward. V0 is inward. What is the direction of V0 cross E? To the right. At this point, this is the direction of E. V0 is still inwards. What is the direction of V0 cross E? To the left.
The factor 2 pi.
That is E. It's not a big surprise because we had said that at least for a point charge that relation should hold. In this system, all the point charges are moving with the same velocity v. So the total magnetic induction will be the sum of the magnetic inductions created by each one of these charges. V0 is a common factor for all of them. And C is a common factor. We can just take it out. What remains is the sum of the electric fields created by each individual charges, which is the total electric field. So this relation still holds. Now let us look at the forces. We already know that on a magnetic dipole it creates a torque. A torque is created by forces. And the force of a magnetic created by a magnetic induction is, well, the general expression for the force, it is Q times E plus V cross B. So this will be the force acting on a point charge in the presence of an electric and magnetic field. Well, in a sense, this also tells us how we distinguish the electric and magnetic fields. So the force acting on a charge in general depends on the velocity of the charge. There is a part that is independent of the velocity, and that part is what we call the electric force. And there is another part which depends on the velocity of the particle, which we call the magnetic force. But now there's kind of a problem. I mean, one of the foreshadowings that we will have. You see, velocity changes if we change our reference frame. Just remember your Galilean relativity. What does Galilean relativity tells us? It tells us that the velocity is a frame-independent quantity. It changes from frame to frame. Acceleration is a frame-independent quantity. As long as you stick with an inertial reference frame, the acceleration is the same in every inertial reference frame. That is kind of the essence of Galilean relativity. Well, if acceleration is the same in every reference frame, then the force should be the same in every reference frame. But look at this expression. If you go to some different inertial reference frame, which has a different velocity, the force seems to be different.
V will be different.
In fact, both B and E, they should be different. Both of them. You see, just changing B doesn't really matter because, let's say, the particle is moving at velocity v. You go to a reference frame which moves with the velocity v. So the particle in that reference frame is at rest. There is no magnetic force acting on it. But the total force should be the same. So E should be different.
Not B.
Also B should be different. Both of them should be different. So that's kind of a foreshadowing of the things to come. You see, if you go to a different reference frame, it won't be a static problem anymore. So our expression for the electric field and the magnetic induction will not be the same. We should modify them. Now, this is something telling us that, oh, okay, we are doing something, but there are certain inconsistencies with our general knowledge of how nature works. You see, if you are not if you don't use this Galilean transformation, properties of Galilean transformation, there's no problem. But when you try to combine your one knowledge in one subject, like electrostatics and magnetostatics, with your knowledge from some other subject, like the Galilean relativity, there's something that's not fitting well. That is something we will need to fix. Now let's look at another problem that we need to fix. You see, this is a problem because we are basically going out of the applicability of our laws. We should be in statics. But if we keep changing frames, we are not really in statics. We don't stay in statics. For example, look at this problem. Not necessarily zero. Look at this problem. If the surface is moving inside itself, nothing is changing. But you go to a reference frame which moves with some velocity in the upward direction. In that reference frame, this plane is moving downward. That's no longer an electrostatic problem. So once you change your reference frame, you are not necessarily in a static problem. That is something we should keep in mind. So that will be the reason of the kind of discrepancy here. Let's look at another such, let's say, discrepancy. Let's look at some charge over here. Let's consider another charge over here. At a given instant. This one is moving upward with some velocity. This one is moving, let's say, in this direction with a different velocity. So each one of them will be creating magnetic fields, and hence they will be exerting magnetic forces on each other. Plus they will also be exerting electric forces on each other. But let's concentrate on the magnetic forces for the time being. What is the direction of the magnetic field created by Q at the position of Q prime? Inward. So this is use your right hand, this is the direction of V, and your finger curls in the direction of B, so it should be inward. Now, what is the direction of the force acting on Q prime due to this B? Yeah, it cannot be outward. It has to be perpendicular to both V and B. It has to be in the screen. But we see V cross B upward. This is the force acting on Q prime. Let's do the same exercise for the force acting on Q. What is the direction of the magnetic field created by Q prime at the position of Q? Outwards. What is the direction of the force? What's the direction of the force? Right. Now, do you see a problem here? Everything we did is correct. Within the, of course, assuming V and V prime are sufficiently small so that we can use, let's say, the magnetostatic approximation. Of course, there will be corrections. But now there's a problem with the third law. The third law states that the forces should be action-reaction pairs. They should be equal in magnitude and pointing in opposite directions. These two forces that these two charges exert on each other, they are not in opposite directions. But the third law tells us that the momentum is conserved, because it tells us that the momentum lost by one is gained by the other one. If you look at these systems, just consider them in the next moment, Q prime will acquire a momentum in the upward direction, whereas Q will acquire momentum in the right direction. The sum, they will acquire a non-zero. The change in their momentum will be non-zero. Although there are no external forces acting on my system, they are acquiring momentum. They are gaining momentum. Momentum doesn't seem to be conserved. So that's another problem that we will be facing. Basically, it will turn out that the magnetic field itself has momentum. So they are actually gaining momentum. They will be gaining momentum, but that momentum will be extracted from the electromagnetic field. Well, those are the things we will look at. But let's see. This is, again, the problem over here is one of the problems at least. This is not a magnetostatic problem. But we can look at a similar magnetostatic problem. Let's assume we have one wire here carrying the current I1 and another wire over here carrying the momentum I2. Now this is a magnetostatic problem. In the above expression, as the charges are moving, the electric and magnetic fields they create will be changing. So that change will reflect in the fact that the magnetic momentum, not the magnetic momentum, the momentum of the electromagnetic field will also change. But this is a static problem. There is no electric field in my system. The magnetic field in my system doesn't change in time. They are all fixed. So we cannot really claim that the electromagnetic field is, the momentum of the electromagnetic field itself is changing, because the electromagnetic field in this problem is not changing. Now, will they satisfy the Newton's third law, the forces that they exert on each other? Now, let's try to write down the forces acting on each other. The force acting on the first loop due to the second loop will be equal to, well, let's just imagine a very small segment over here. Or first, let's study what is the force acting on a wire. We already said that this is the force law. So let's assume a wire in a region where we have some magnetic field. Let's consider this very small segment, which is carrying a current I. Of course, this I is due to the motion of the charges. Or in fact, it will be lambda times V. This will be the magnitude of that thing. Now, each charge will feel a force, assuming that ignoring the electric field, it will feel a force QV cross B. B is our external field.
Lambda is the number density of the charge.
Linear density.
It doesn't have to, it can be Newton. The wire can be Newton.
Lambda is the linear charge density of the moving charges. You see, the total current density will basically be lambda in an actual, let's say, in a metal. The charges that are moving are negative charges. The electrons, they will be moving with a velocity v. Plus, there's also the velocity of the positive charges. Let's say they will be moving with velocity v plus. But if you are in the reference frame in which the wire is at rest, the positive charges are not moving. So Vp is 0. Of course, we also have the suitable Dirac deltas. This will be the actual form of the current. But since the positive charges are at rest, we only have the electrons moving. Also, in the above expression, lambda is the linear charge density of the moving charges, because they will be the ones that are creating the magnetic field, magnetic induction field. So dF is Q, let's say Qi V cross B. This is the force acting on a single one. So if you just sum over all the charges in your wire, this will be basically your the total force acting on that very small segment of the wire. But Qi times V is nothing but J. Let's say Ji. Ji, the sum over Ji is the sum of all the current running through my wire, but that is nothing but lambda, or let me write it in this form, I times dl cross B. Well, I is the number of charges passing through the cross-section of my system per unit time. If I multiply it by dl, it is basically the total charges in that very small volume multiplied by the velocity. But that is nothing but my J. Or sum over Qi times V. I just assume this small volume. I'm summing over all the charges in this very small length, dl. They will be, let's say, passing through this the length dl in a time dt. So I is basically the total charge is dq over t. Well, dq dq over dl times dt over dl, lambda times v. Yes?
So basically we are integrating over the area of the wire, but we can't express it that way because we took the limit as the thickness is it.
Yes. So this will be the force law, the force acting on a wire in a current carrying wire in a magnetic field. Well, experimentally this was the right force. But this is easy to measure. You cannot really measure the magnetic force acting on a point charge. But you can measure the force acting on a wire. And from this law you can just go back and go to the expression for the force acting on a point charge. Now let's go back here, this problem. The force that they exert on each other. Well, if it doesn't satisfy the Newton's third law, then we will be in trouble. Because in the case of two-point charges moving in different directions, we could say that, okay, the electromagnetic field is changing, so it's basically changing the momentum of the electromagnetic field, which explains the change in the momentum of my charges. But in this problem, my electromagnetic field is not changing with time. Everything is static here. So if there is a momentum of the electromagnetic field, it's not changing in this problem. So if I have anything called the momentum conservation, then the forces that these two wires exert on each other should be the same, just in opposite directions. So let's say this is our dl. No, sorry. dl is pointing in the opposite direction. This is dl, because this is the direction of the current. So that piece will feel a force which will be given by I1 times, let me call it dl1. dl1 cross B1, B2. B2 is the magnetic field created by the second wire at the position of dl1. So the total force that the first wire will feel due to the second wire will be equal to I1 dl1 cross B2 integrated over all my wire. Now let's look at B2. We already know what B2 is. dB2, that is if we just assume a very small segment over here and call it dL2, and then dB2 will be just 1 over C I2 times dL2 cross, let me use this symbol, delta 1, 2, hat over delta 1, 2 squared, where this delta 1, 2 vector is R1 minus R2. R1 being the position of my dL1, R2 being the position of my dL2. This is nothing but the Biot-Savart law that we wrote before. Now I can write F12. Again, this is the force acting on the first wire due to the second wire. This will be equal to 1 over C I1 times I2 integral of dL1 cross integral of dL2 cross delta 1, 2 hat divided by delta 1, 2 cube. Of course, here I have a double integral. Cube, yes. Square, square. So I'm integrating over both of these closed wires. Now let us simplify it a bit. We remember this expression. What is it equal to? Well, if you don't remember this, just using index notation, it's just a couple of lines deriving it. But after you write it, let's say 20 or 30 times, you remember. So F12 would be equal to 1 over C I1 I2, our double integral dL2 times dL1 dot delta 1, 2 over delta 1, 2 squared minus, yes, or let's make this hat, minus delta 1, 2 hat divided by delta 1, 2 squared dL1 dot dL2. Let me rewrite it, 1 over C I1 I2, this double integral dL1 dot dL2 delta 1, 2 hat divided by delta 1, 2 squared. This is with a minus sign, plus 1 over C I1 I2 dL2 dL1 dot delta 1, 2 hat divided by delta 1, 2 squared. Well, the first one is nice. You see, this is the force exerted on the first wire due to the second wire. Later on, we will compare it with the force exerted on the second wire due to the first wire. But to calculate that force, the derivation will be identical, just change 1 and 2 everywhere. If you look at the first term, dL1 scalar product dL2, if you exchange 1 and 2, it doesn't change. Delta 1, 2 squared doesn't change. Delta 1, 2 hat is replaced by delta 2, 1 hat, but those differ by a sign. So if the force was only the first term, then the forces that each wire exerts on each other is just have the same magnitude, just opposite in direction. They differ by a minus sign. But we have the second term. Now let's look at the second term. You should be able to say what this is equal to. Imagine we multiply this with Q. What is Q times delta 1, 2 over delta 1, 2 hat over delta 1, 2 squared?
Yeah, divergence of beta field.
Well, if we would replace this multiply by Q, that delta 1, 2 hat divided by delta 1, 2 squared is nothing but the electric field created by a point charge at the point R2. Well, there's the minus sign.
It's the curl of the electric field.
So this will be equal to integral over an area of the curl of delta 1, 2 hat divided by delta 1, 2 squared, but that curl is 0. So the second term is 0. And hence we end up having the force that two wires exert on each other. This is 1 over C I1 times I2. This double loop integral dl1 dot dl2 delta 1, 2 hat divided by delta 1, 2 squared. And it does satisfy Newton's third law. So whatever magnetic momentum one wire would acquire, it will be the same for the other wire in the opposite direction. Of course, if we just let them move, in that case, it's no longer statics. So things will be much more complicated, but nevertheless, with these action-reaction force pairs in our actual magnetostatic problem does hold still. But when we start to leave the magnetostatic domain, we kind of have an idea that we will be having problems. That is something we will resolve later on when we start dynamics. Now, any questions on this one? Now, questions?
Can you go Lorentz force? What is the unit of E?
Now it's correct. Good. Let's continue with the Lorentz force, but this time let's look at the work. We have time. Well, if you just imagine that the charge is slightly displaced, then the work done is just moving around. Work done would be F dot dl. This is equal to Q times V cross B dot dl, which is Q times dl over dt cross B dot dl. But you see, dl cross B is perpendicular to both B and also dl. So that dl cross B is perpendicular to dl. You are taking its scalar product with dl. So if you just take the scalar product of two vectors that are perpendicular to each other, the scalar product is 0. Which tells me that the magnetic force does not do any work. There is no work done by a magnetic force. Let us look at an example. Let us assume we have a region of where the B is non-zero, even uniform. We put some wire, attach some mass, and send some current through the wire, let's say in this direction. So what will be the direction of the force acting on our wire, on the wires, let's say? At the top segment, remember the F is I over C, V cross B. Upward. Here. Here on the opposite side. To the right. So the left and the right forces will cancel each other if the magnetic field is uniform. And I'm also assuming that part of the wire is out of the region of magnetic field. So only the top part is in the region of the magnetic field. So there will be an upward force if the total width is, let's say, L. The force that the wire will feel will be, no, sorry, this is dl. Are the units correct here? Well, let's see. The unit of I over C dl cross B, it is the unit of I over C is unit of Q divided by the unit of time, unit of length divided by the unit of C times the unit of B. Well, the unit of B times the unit of Q, remember unit of Q is it? Is the force. So the unit of force is equal to unit of L over C times T times the unit of force, which is correct. L over T has the units of velocity, C has the units of velocity, they cancel, so the units are fine. Okay, so the total force acting, the total magnetic force acting on my wire will be just I over C times the length L times whatever the magnetic field is. Or let's say I0. This should be equal to mg. So if I0 is equal to mgc over B times L, then the mass will be at rest. The upward force of the magnetic field will balance the downward gravitational pull on my mass, ignoring the mass of the wire. So it will just suspend in midair. Now let's assume for the time being that we send a current through my wire larger than I0. So what will happen to the upward force? Will it increase, decrease, stay the same?
Increase. It will overcome the weight.
It will overcome the weight. So the wire will start moving upward. Well, we have a magnetic force in the upward direction. We have a displacement in the upward direction. So there is work done. there is a positive work being done by
by the current. And the source of the potential is the current.
Well, basically, yes. You see, it's still not the magnetic field doing the work. What is actually happening? Without any motion, if the wire is at rest, this will be the velocity of the charges creating the current. But now the wire is moving upward, let's say with a velocity u. So the total velocity of the charges in the wire will not be horizontal, they will have a vertical component. So this will be the total velocity of those charges. But the magnetic field is perpendicular to this velocity. So the magnetic force. So this is the magnetic force. Well, this force has a vertical component and also a horizontal component. And the horizontal component is in the direction as to stop the current. So if there are no other effects, the magnetic force will stop the current. You cannot have a larger current. So if you want to have a larger current, a current larger than I0, something should be pushing the charges. And that is basically the electric field that is supplying the current, or the battery that is doing the work. What the magnetic field does is essentially it is changing the direction of the force. Well, the electric field, the battery is doing the work, pushing the charges along the wire. And the magnetic field is kind of changing the direction of that force in the vertical direction, hence that force is doing the work. Now let's look at it from a microscopic perspective. Yeah, this was kind of the beginning. So you see the magnetic field is not exerting any force on the wire, it's exerting force on the charges. So you see you are forcing the charges to move in this direction. So what will be the force acting on this charge? This is the direction of the motion of the charges. The magnetic field, let's say it's into the screen. It will be pushing it upward. So the trajectory of this charge object will be, it will move up. It will curve upwards. But then it hits the boundary of the wire. So it is the wire just exerts a force on this charge to keep it within the wire. But it's like a potential wall problem in quantum mechanics or classical mechanics. The charges are free to move as long as they are inside your box. When they hit the boundary of the box will exert a force on the charges, causing them to bounce back. But this means the charges are exerting forces on the wire. So this is basically what is happening. You have this electric field driving the charges in this direction. It is doing work on our charges. So the charges are accelerating, they are gaining kinetic energy. The magnetic field does not do any work on the charges, but it bends them upward. Let's say in this configuration, it will bend them upward. So the electric field causes them to gain energy. They will hit it upward. Once they hit the boundary of the surface of the wire, they will bounce back, exerting a force on the wire. And if the more work that the electric field does on the charges, the more force they will exert on the boundary of the wire. And hence, basically, through this method, it's the magnetic field that is converting the work done by the battery on the charges, causing it to transfer it into the wire as a whole. Now, what about the trajectory of these point charges? Okay, we said that this will be the trajectory. They should be just curving upward and then down and up and down, etc. Now, let's be more quantitative. Well, eventually we are physicists, right? So we have to be more precise. This is what we expect. So let's solve it. Let's start with a simple problem of a point charge. In a uniform magnetic field. Say we have a plus q charge moving in this direction with a velocity v. What is the direction of the force acting on this? Upward. So as the particle is moving, will its speed change? No. So it is moving with a constant speed. The force is always perpendicular to its velocity. What kind of motion it will do? Uniform circular motion, not just circular motion, it will be uniform. And so it will basically go around such a trajectory with radius r. What's the magnitude of the magnetic force? Q V over C times B. This is the magnitude of the magnetic force. This is the force that is providing the centripetal force, which should be mv squared over r. So this is how the radius is related to the other properties. Or let's say if you have the radius, let me just, V's I can just cancel. Q over m is equal to V times C over R times B. So for example, if you have a particle that is going in, if you have a region of space which has a uniform magnetic field, and if you look at the particles, how they move in that region, well, you can measure their speed if you determine their position as a function of time. So you can actually measure V. Well, C is just a constant, a known constant. R you can just measure by the curvature of the path. B is the magnetic field that you create. So by just looking at the path, you can determine the charge over the mass ratio of this particle. In particular, you can determine whether it is a positively charged and a negatively charged object. That's kind of the easiest thing to determine. You just need to look at which way does it bend. So in this case, since the object is bending upward as it's moving in our region, we know that it is positively charged. If it would bend downward, then we could say that it is negatively charged. So this is one way how you measure the properties of particles in accelerators.
We said that for this force, for this formula of the force to be valid, we shouldn't have an acceleration.
No, the expression of the force is valid even if there is an acceleration. You see, this Lorentz force, as far as we know, let's say, this expression of the force is always valid. If you know the electric field, if you know the magnetic field in a given region, and if you send a charge in that, this will be the force it will feel. Always. Whether it accelerates, decelerates, it doesn't matter. So you see, at least in this case, we assume that there is no component of the velocity in the direction of the magnetic field. So in this case, it just makes circles. If it also has a component in the direction of the magnetic field, Well, there won't be any force in that direction because the force, since it is V cross B, the force is proportional to V cross B. The force is always perpendicular to B. So it doesn't have any component in the direction of B. So if there is a velocity component in the direction of B, it will just stay the same. So in that case, if we have a region of space which has some magnetic field, and if initially there's some, it will make circles around this magnetic field lines, but at the same time, if it has a component of velocity along the direction, it will just move also along the direction of the magnetic field lines, creating a helix. So it will basically move in this direction, assuming it has a upward initial velocity component. Now let's consider a space, a region where the magnetic field is not uniform. So let's say you have some magnetic field here, some other magnetic field here, denser. It gets stronger. So initially you send a particle. Let's say negatively charged. What will be the direction of the force? So at this point, no force acting on it. The magnetic field is negligible over there. But let's say now it came over here, towards the right. The force gets stronger, still pushing it vertically away from your region. So this will be more or less the trajectory. Because as it approaches the region of a larger magnetic field, there will be a larger force. Well, you can do the same thing for a positive charge. Its trajectory will be a bit more complicated because it will just come here. The force will be in the other direction, so it will bend the curve in the other direction. But the force gets larger and larger as it approaches the larger magnetic induction region. So this will be more or less the trajectory. In any case, basically the charges will be moving away from regions of larger magnetic field. Well, this is the basis of magnetic confinement. So, for example, in nuclear fusion experiments, they are trying to fuse nuclei, just like they do in the sun. Well, in the sun, there is a high pressure, high temperature. And so under these conditions, under high pressure and high temperature just means they're under high pressure, which means they are very dense. High temperature means they are moving also fast, so eventually they will just hit each other, actually the nuclei will hit each other. Well, there is the electromagnetic barrier. Due to the electromagnetic force, they will be pushing each other, so they should be coming very close to each other for the nuclear forces to take over. But once they approach to each other, once they come very close to each other, the nuclear attractive forces will be much larger than the electromagnetic repulsive forces, so they just bind together. In this process, they release energy. But the problem is, for example, in the sun, this high density region, high pressure region is created by gravity. So it basically holds all those mass, all that hot mass in a very small volume. But on Earth, the gravity is not enough. So we have to put them in some container. but no container can bear that high temperatures. So we have to keep them under what's called the magnetic bottles. So this hot gas shouldn't touch the containing material. So we try to confine them within such a magnetic walls. Now then the problem is, if you have this plasma, which is itself made up of charges moving around, so you apply an external magnetic field, but these moving charges also create their own magnetic field, and so it's hard to keep this magnetic bottle stable. It just disappears due to the induced currents. So that's one of the most difficult things in the plasma fusion studies. Well, another interesting phenomena, well, then we can go. Let's say Earth. Earth has its own magnetic field. Which pole of the Earth is on the North Pole? Which magnetic pole is on the North Pole? No, South. You see, the North Pole of magnets is attracted to the magnetic pole on the north. This is the magnetic field of Earth. Here you have the sun, which constantly sends charged objects in our direction. So let's see, they arrive here. There is a region of magnetic field. So they will start curling around the magnetic field. Well, they have a direction in the opposite direction of the magnetic field line, at that region at least. So they will start curling in this direction. Well, they are approaching regions which has a larger magnetic field. But we just said that the charges will basically feel a net force away from the regions of larger magnetic field. So they will come here. They will bounce back. So these charged regions will basically be trapped in this belts. They should be 1 Allen belts. All these charged particles, they are basically sent to the poles. And do you know something famous about the poles, except that their cold temperature? North, polar lights, or auroras. This is the cause of those lights. Basically, all these charged particles are sent to the poles, and there's a large density. They collide with the atoms in the atmosphere. They excite them. When they de-excite, you have all these nice light shows. It's also another problem for us, because this region is called 1 Allen. I think they're called the 1 Allen belts. It's a highly radioactive region. If you want to put some satellites there, they should better be strong enough to resist that radiation. Anyway, any questions? It's basically, I mean, in modern physics, you didn't take modern physics. Did you take quantum physics? You did. There are all these, in the atomic spectra, there are all these transitions. So the color is basically determined by the fact that our atmosphere is dominantly nitrogen and oxygen. So those colors correspond to atomic transitions in nitrogen and oxygen.
When you are drawing it, you showed us that they are oscillating from one photon, and is that how it goes? Why did it go back?
Well, because you see, at the poles, the magnetic field is stronger. Well, the description is not really as simple as this one, but you see, look at here, what's happening. As the charged object is moving to a region which has a stronger magnetic field, it is pushed away. Well, the same thing happens over here. You see, all these magnetic field lines are basically going to a point. Although initially it had some velocity in the perpendicular direction, but when the magnetic field lines goes to a point and converging to a point, Well, none of the components is really perpendicular to the magnetic fields. So effectively, the magnetic field lines are bending. So the force that they exert is also changing its direction. So it's due to this changes in the direction of the magnetic field, they create a force in the opposite direction on the average, just pushing it backward. So that is what it causes it. I mean, in these regions, the magnetic field is more or less uniform. But the closer you are to the pole, it's no longer uniform. Any questions? Have you seen your homework? Okay. Well, you had already seen it in weeks 6 or 7, but I just wrote it in PDF this time. I put it in Note to class.